Hello. We will now continue with some more practical issues. We ended up the previous presentation by explaining that some of the matrix elements were calculated in a real space grid of uniform points. That means that the integrals and therefore the total energy will depend somewhat on the position of the basis orbitals relative to the grid points. And this is called the egg box effect because it creates a fictitious potential with the shape of an egg box depending on the position of the atoms. To ameliorate that, SIESTA allows to perform what we call grid cell sampling by calculating the matrix elements at different positions of the atoms relative to the grid points. An important factor of accuracy in SIESTA is the fineness of the grid used to integrate the matrix elements. And we measure this fineness by the maximum energy of a plane wave that can be represented in that grid, and which is given by this simple formula as a function of the grid spacing. However, it is important to understand that the mesh cutoff used in SIESTA is different from the plane wave cutoff of a plane wave basis. In the latter, increasing the cutoff of the plane waves increases the number of plane waves and always leads to a decrease in energy. In SIESTA, increasing the mesh cutoff of the integration grid can either increase or decrease the energy, so the convergence is not always from above. Another important issue is Kpoint sampling, which means nothing but integrating in reciprocal space. In a solid, the wave functions are characterized by a plane wave vector k, which characterizes the block functions. And we need to integrate over the Brillouin zone, what in practice is done in a grid of uniformly separated points is in real space. Because of symmetry, some points are equivalent, and we need to integrate only over the irreducible part of the Brillouin zone, which is here shown by the blue points. Monhorst and Pak noticed that if you displace the grid points relative to the origin, the degeneracy of the points increases and you need fewer points in the irreducible part. In any case, the accuracy of this integration is characterized by the fineness of the grid, as in real space, and so by the separation between the grid points. So we do something similar as in real space, and we characterize the fineness of the grid by vector in reciprocal space, that is in real space, given by this relationship as a function of the mesh separation, and we call it the length cutoff. By increasing the length cutoff, you increase the number of grid points and the accuracy of the integration. We have already explained that some matrix elements involve the integral of a potential over the overlap region between pairs of basis orbitals. If the system is finite, there will be only one such overlap region between two basis orbitals. However, if the system is periodic, there will be repetitions of the basis orbitals in each unit cell, and there will be different regions of overlap between pairs of basis orbitals, in this case the orange one and the red one. If only the so-called gamma point, so k equals 0, is involved, then the phase of the wave function in different repetitions of the unit cell will be the same, and we can simply add the integral over the different overlap regions. However, if we are performing K-point sampling, the phase factor at the different unit cells will be different, and the different overlaps will have to be multiplied by different phase factors. That means that we need to keep track of different overlaps between the same pair of basis orbitals corresponding to different repetitions of the unit cell, to be multiplied by different phase factors for different k vectors. What SIESTA does is to increase the unit cell into a larger supercell and to repeat the basis orbitals as if they were different in the whole supercell. And it calculates the overlaps between the different repetitions of the basis orbitals. This supercell is in principle transparent to the user, but it is all the time working inside the program. We have already explained that SIESTA assumes that the system is periodically repeated, that is, periodic boundary conditions. This is true even for systems that are not really periodic, like molecules. And it allows to solve Poisson's equation, that is, to find the potential, the electrostatic potential from the density using fast Fourier transforms. What one does is you Fourier transform the density, and then the Fourier coefficients of the potential are related to those of the density by this simple relationship, and then you Fourier transform back to real space. This has some consequences. First, if the total charge is not zero, that is, if the system is charged, then the Fourier coefficient for g equals 0 is not 0, and Vg becomes infinite. What is simply reflects that the potential will be infinite for an infinite repetition of charges. So what SIESTA does in that case is to compensate the net charge by a uniform background of compensating charge. The second consequence is that if you have dipoles or of course net charges in the system, then this will induce a spurious interaction between different images of the charge in different unit cells. So you have to take this into account in the case of systems with charge or dipoles. Another issue worth mentioning is how SIESTA calculates the exchange and correlation potential. In DFT, the exchange and correlation potential is the functional derivative of the exchange correlation energy, which in the GGA approximation depends on the local charge and the gradient of the local charge. When one performs this functional derivative, the results depends not only on the density and its gradient, but on higher order derivatives, and it is a rather complicated expression. So what SIESTA does is to calculate the gradient using finite derivatives from the density itself, using some higher order derivatives, but let us simplify it with a first order derivative with this formula. And then once you have calculated the gradient using the density at the grid points, you will have the expression for the exchange correlation energy as an integral over the grid points, and therefore as a function of the density at the different points. That means that the expression of the exchange correlation energy will be a normal function of the density at all points rather than functional, and that the exchange correlation potential can be calculated as a normal partial derivative of the energy at the different points with respect to each particular density at each point. Since, as explained previously, the energy is a complicated expression with many terms depending on many matrix elements, the forces and stresses, which are the derivatives of the energy with respect to the atomic positions or the formations of the unit cell, also have many terms. In SIESTA, the philosophy is that each time you calculate a matrix element or a term that depends on the, is in the energy, you also calculate the its derivative with respect to the atomic positions and the formation vectors. For example, a matrix elements of a potential V between two pairs of basis orbitals can be written in this way. And because the phi orbital is a function of r minus rv, this can be rewritten as a matrix element between the basis orbital and the gradient of another basis orbital. This is important, or this contributes also to the forces, because when you move an atom, you also move the basis orbitals of that atom, and this contains some terms in the forces which are called Poulet forces, and in SIESTA they are calculated with the rest of terms and included automatically in the forces and stresses. Of course, all these can be done only in the last self-consistency iterations, that is when you have already converged the density. Also regarding the stress, or in particular the pressure, that is the derivative of the energy with respect to the volume, SIESTA prints two pressures, which are called solid pressure and molecule pressure. This refers to two possible definitions of pressure, that is, of the derivative of the energy with respect to volume. If you increase the volume of the unit cell, you could do two different things with the atoms. In a solid, what you would expect is that the atoms or the interatomic distances increase with the volume of the unit cell, so that the relative shape remains the same. In a molecule, however, you would expect that as you increase the volume of the unit cell, the molecule does not expand, but the distances remain the same. This doesn't mean that the pressure is zero, because there may still be some interaction between molecules in two different repetitions of the unit cell, but of course you would expect the pressure to be much less than if you expand the molecule with the unit cell. And let us finish with something which is frequently the nightmare of the DFT practitioner, which is the self-consistency convergence. We have already seen that we have to perform a self-consistency cycle in which you start with some density, you calculate a potential, and from that potential you solve Schrödinger's equation, and you calculate a new density. And you have to iterate this until the final density, or the new density, is equal to the input density. In practice, what happens is that this simple cycle does not converge, so that the density gets wild. So a simple procedure is to, in the new iteration, to start not with the new density, but with a mixing of the old density and the new density. And the weight of the new density is referred to as the mixing weight, and typically it it has to be only a few percent for the cycle to converge. The reason, or the main reason for the divergence of the self-consistency cycle is the phenomenon of charge sloshing. If you have, let's say, a system composed of two subsystems, and most of the charge is, let's say, in the system 1, so that the density here is large and the density here is small, then because of Coulomb repulsion, the energy of the states in this system will be larger than those in this system. So the energy scheme will be like this. If the Fermi energy happens to be in between the two states, this state will become charged because it is below the Fermi level, and this will become empty. And then in the next iteration, the charge will go from here to here and will be like that. And of course, this will, in the next iteration, repeat, and you will get a divergence of this process instead of convergence. One simple way of moderating this is to increase the electronic temperature. So not to fill the states strictly if they are above or below the Fermi level, but to weight them with Fermi-Dirac weight, so that both of them will be partially occupied. Another way of facilitating the convergence of the self-consistency cycle is to use a more sophisticated mixing scheme. And what we typically use is the so-called Poulet mixing. If you have some input density at the nth step of the cycle and the output is rho nu, we can define the difference between the output and input densities as the residual difference. Now, what you would like is that the residual would be 0, because then the output and input densities would be equal and you would be finished. So what you can do is to generate a new density for the next step, which is a combination of m previous densities. And you do this by minimizing the size of the expected residuals, where you expect that the expected residual will also be the same combination of the previous residuals. So you choose this coefficient Ck to minimize the residual of the next iteration, and you input them in the new density. If you do strictly this, then you will not really evolve, because your density will typically be stuck in the same set of previous densities. So you have to somehow also mix it with some part of the output densities and not only of the input densities as written here. So you will also have a mixing weight for the output part of the densities. Okay, and with this, we finish this second presentation, and I wish you a nice rest of the course. Thank you.